Welcome once again in the class of topology, and today we are going to start the new chapter, that is covering and compact spaces. So you need to be a little bit careful as it is a new chapter. So first we will define what is a covering, what is an open cover, what is a finite cover, what is a infinite cover, what is subcover, what is basic cover, what is sub-basic cover, what is compact set, and then we'll move on to the theorems. So first of all, what is a cover? So if a collection of sets, say C, containing, definitely it is a collection of sets, so it will contain some sets. So let it be Gi, where I belong to a particular family lambda. So if a collection of sets, say C, covers is subset A of a topological space X, then this C, the collection C, is called a cover of A. In particular, you can say if C covers X, then C is a cover of X. So what is meaning of covers a set? Covers a set means A is, that means you can say A is a subset of union of members of C. So A is a subset of Gi, where I belongs to that particular family lambda. So if C covers X, then definitely X will not be a subset, but in fact it will be union of Gi for I belonging to the family lambda, and in that case C will be called cover of the topological space X. Further, if each set in the collection C, if each Gi is open, then it is called an open cover. Then it is called an open cover of A. Or in fact, if it is covering X, then it will be called an open cover of X. Furthermore, if the number of members of C is finite, then C is called a finite cover of A or a finite cover of X. This is the definition of covering. Moreover, if every member of C, that means every Gi, is a basic open cover, is a basic open set, if each of these Gi is a basic open set, then C is called a basic open cover of A or a basic open cover of X, whatever the case is. If every member of this collection C, that means every Gi, is a sub-basic open set, then C is called a sub-basic open cover of A or a sub-basic open cover of X, whatever the case will be. So these are the definitions of covering, open cover, finite open cover, basic open cover, sub-basic open cover, etc. So these are the basic definitions, and now we are moving towards the main definition of this chapter, that is a compact set. What is a compact set? So here you have to give some attention, because this is the basic definition and whole of the chapter will depend upon this definition. So the definition is, let X top be a topological space and A is a subset of X, then A is said to be a compact subset of X, compact subset of X, if every open cover of A has a finite subcover. So what it implies, what is the meaning of this sentence? Let us understand a little bit clearly. So there is a family C of open sets in topology TOP, say Gi, where I belong to a particular family lambda. So it is an open cover, is an open cover of A, and if A is to be compact, then we must have a subcover of this, a finite subcover of this cover C. I'll explain more clearly. So here C is the open cover. That means A is covered by the members of this collection. So A is a subset of union Gi, where I belongs to lambda. That means A is a subset of union of members of C. So C is a cover. Now C has a finite subcover. C has a finite subcover means here the number of members may be infinite, but sometimes it happens that we don't need each member to cover A. There are a finite number of members of this collection which can cover A. Suppose this collection, I'm naming it as G1, G2, G3, G4 and so on. Suppose some of the members G1, G7, G9, G11, G25, G37 are enough to cover A. That means A is a subset of, in fact, it is true that A is a subset of union of Gii belongs to lambda, but A is also covered by only these members. So G1, union G7, union G9, union G11, union G25, union G37. So these members, only 6 members suppose, can cover A. So that means the collection of these open sets, so name it as C star. So that means the members of C star can cover A. Then we say that because every member of C star is coming from C, that means C star is a subset of C, and C was the main cover, open cover of A, and C star can also cover A. That means C star is a finite subcover of C. It's not a subcover of A, because like you are having subgroup. So subgroup of what? Subgroup of group. If you are having subset, so subset of what? Set. Subset of set. Similarly, subcover of what? Subcover of cover. So C star is a subcover of C. It is not a subcover of A. So if every open cover of A has a finite subcover, then A is said to be a compact subset of X. On the same lines, you can say that if every open cover of X, I'm not talking about A now, I'm talking about the whole space X. If every open cover of X has a finite subcover, then we will say that the topological space X top is compact space. So this was the definition of a compact set and a compact space. And now we will move on to a basic properties of compact sets. So here comes the first one. First of all, every finite set is compact. This is the first property. So first theorem you can say, every finite set is compact. And it is, I think, clear. It is very much obvious. But let us prove it. Let us see how the proof goes. So I am starting with the proof. Let X top be a topological space. Let X top be a topological space. Let A, because I'm talking about finite set, so A must be finite. So let members of A I'm denoting by x1, x2, x3 and so on, xn, subset of x be a finite subset of x. I have taken a topological space and a finite subset of the topological space x. Since I am to prove that every finite set is compact, I'll have to show that A is compact. For that, what I'll have to do, I'll have to take one open cover of A and I'll have to find some finite subcover of that particular cover. So let's see collection containing sets Gi where I belongs to lambda be an open cover of A. So I have taken an open cover of A, an arbitrary open cover of A, and I'll find a finite subcover of this open cover. And if I can find that finite subcover, that means the set A is compact because it is an arbitrary open cover, and it will imply that every open cover has a finite subcover. So this is an open cover of A. Open cover of A means A is covered by union of members Gi where I belongs to that particular family lambda. Now I'll take one by one. So let us start with x1. x1 belongs to A and A is a subset of union of Gi, I belonging to lambda. That means x1 also belongs to this union. And if x1 belongs to this union, then x1 must be in some particular Gi. So let Gi1 be the set in which x1 is there. I am taking I1 to be the minimum among all i's to which x belong, because x1 may be in several Gi's. x1 may be in Gi1, maybe in Gi2, maybe in Gi3, maybe in several Gi's. So I am taking the smallest I1 such that x belongs to Gi1. So let I1 be the smallest suffix. Let I1 be the smallest suffix such that x1 belongs to Gi1. Similarly, let I2 be the smallest suffix such that x2 belong to Gi2 and so on and so on. Now consider this collection C star. Consider C star having these sets Gi1, Gi2, Gi3 and so on, Gin. Since your x1 is in Gi1, your x2 is in Gi2, your x3 is in Gi3 and so on, your xn is in Gin, that means whole of the set A is contained in the union of these sets. So you can say then your A is a subset of union of these Gij's where your J is moving from 1 to n. But this Gi1 member of C star, this is from where we have taken this. This we have taken from union of Gi I belonging to lambda. That means this Gi1 is coming from C. Similarly, this Gi2 is coming from C. This Gi3 is coming from C. This Gin is coming from C. That means your C star is nothing but it is a subset of your C. C star is a subset of C. C was open cover of A. But C star is also covering A. That means C star is a finite subcover of C because it has finite number of members. We have taken an arbitrary open cover C and we have obtained a finite subcover of that cover. That means every open cover of A has a finite subcover. That means the set A is compact, and A we have taken to be a finite set, and it proves that every finite set is compact. And that was our first theorem, our first result regarding the compactness, regarding the covering spaces, or regarding covers, open covers and subcovers. Then I am taking another theorem. So next theorem which I am going to take is every closed subset of a compact set or compact space is compact. If a set is compact, or if a space is compact and we are taking a closed subset of it, then that particular closed subset will also be compact. That is the next result what we are going to prove today. So I am starting with the proof now. Let X tau be a compact topological space and let B subset of X be a closed set. So what I have taken? I have taken a compact space and an arbitrary closed subset of X, and now I'll prove that B is also compact. So I'll prove that B is compact. For that, what I'll have to do, I'll have to take B is to be closed, and we have to prove that it is a compact. So I'll have to take one open cover of B, and then I'll show that it has a finite subcover. So let C containing G1, Gi you can say, Gi, I belonging to lambda, be an open cover, be an open cover of B. So B is a closed subset of a compact set, and I have taken an open cover of B, and now I'll find a finite subcover of this cover C, and that will show that B is compact. C is an open cover of B, means your B is covered by union of members of this C. That means union of Gi, I belonging to that particular family lambda. So if B is a subset of this, then B union B complement is a subset of this union B complement. I have taken union both sides with B complement. And what is B union B complement? It is nothing but the whole space X. B union B complement is nothing but the whole space X. X is a subset of this, definitely means X is equal to this because X is the whole space. Every member in the first union is an open set, and B complement is also open because B was closed. So that means this collection B complement and GIs, where your I is coming from lambda, this collection C1 you can say, this implies this C1 is an open cover, of X now, because union of members of C1, now they are covering X. But what about X? Your X is given to be compact. X is compact and you are having an open cover of X, that means there must be some finite subcover of this cover. So definitely that means there exists a finite subcover. So therefore there exists a finite subcover, and since it is C1, I am naming the finite subcover as C1 star, and B complement I am putting it in, and then I'm taking some G1, G2, G3 and Gn, because it is a finite subcover, so the number of members must be finite. So let there exist a finite subcover C1 star of C1. C1 was an open cover of X and X was compact, so therefore there exists a finite subcover this of C1. It's a finite subcover. What it means that this open cover is sufficient to cover the space X. So this means your X is covered by union of these members. So you can say B complement, union G1, union G2, union and so on, union Gn. Now look that this is X covered by this. So you can say X is equal to, because X is the whole space, need not put the sign of subset, you can say X is equal to this. Now this X is this and B is a subset of X. B is a subset of X, that means B is automatically covered by this union. And since no part of B is covered by B complement, so you can delete B complement from here, because no part of B will be covered by B complement. So that means B is covered by this. But these G1, G2, Gn, from where they are coming? They are coming from G. Sorry, they are coming from C. So that means the collection G1, G2, G3, Gn is a finite subcover of C. Subcover of C. So I am naming it as C star. B was a closed set. You have taken an open cover C of B and now you have obtained a finite subcover of C. That means the set for which you have taken the open cover B is compact. So this means B is compact. So what the result we have proved now will be used in coming theorems, and it is a very important result that closed subset of a compact space is compact. This result we have proved in this theorem, and we will use this result widely in the coming theorems. So let us move on to the next theorem. I am going to take the next theorem. Next theorem is prove that every compact subset of a Hausdorff space is closed. Now this is the theorem. Since you have seen my previous videos, you know what is a Hausdorff space. And now we have to show that if you take a compact subset of a Hausdorff space, then it will be closed. So from where we have to start, let X tau be a Hausdorff space, that means T2 space. I have taken a Hausdorff space and I'll take a compact subset of it. So let A be a compact subset of X, and now I will show that this A is a closed set. And to prove that A is closed, it is sufficient to show that its complement is open, and that is easier for us to prove that the complement of A is open. So we will show that complement of A is open, and complement of A is open will clearly imply that A is closed. To show that A complement is open, what we will have to do, let X be an element of A complement, and we will try to find an open set G such that X belongs to G and G is a subset of A complement. We will have to do that, because if we can find an open set G satisfying this, then your A complement will be open, and A complement open will automatically imply that A is closed. You have taken X belonging to A complement. Therefore, for every Y belonging to A, now look at what I am doing. Here is your X, here is your A, and then A complement. You have taken X from A complement from here, and I am taking Y from inside A. Since X is in A complement and Y is in A, then X cannot be equal to Y, because one is from A and another is from A complement. How can they be equal? So X is not equal to Y. And your space is Hausdorff. And if the space is Hausdorff, you are taking two distinct points. Definitely there will be a pair of disjoint open sets, one containing X and other containing Y. So therefore there exist open sets, or you can say neighborhoods of X and Y. There exist open neighborhoods of X and Y, say mx and ny, such that mx intersection ny is equal to phi. Now what I will do, next step, I'm going towards, I'm not rubbing this diagram as it will be useful to understand the theorem more clearly. Now I'm taking all the ny's for every y belonging to A. So let C be the set, C be the collection of ny's for every y belonging to A. That means what we have done, we have taken an open cover of A. For every member of A, I have taken an open set containing that. Open neighborhood means open set. So for every A, if there is Y here, I have taken an open set, here I have taken an open set, and like this. So what I have taken an open cover of A. For every element of A, I have taken ny. And on the other side, for every y, there will be ny and there will be mx. What I will do now, I will take union of, let, one thing is clear, that C is an open cover of A. So let me write that first. Then C is an open cover of A. That means your A is covered by union of these ny's where y belong to A. So A will be subset of union of ny's. On the other side, this A is compact. This A is compact. This is given because it was in the starting given that compact subset of Hausdorff space. So this is compact. If it is compact and it has an open cover, so definitely there will be a finite subcover. So therefore there exists a finite subcover C star, and it will have some finite number of members n y1 n y2 and so on, say n yp of C. Since A is compact, open cover of A will have a finite subcover. Now A is covered by union of these members. is covered by union of these n y i's, where I vary from 1 to p. On the other side, corresponding to each n y, there is one mx. So for n by 1 there will be mx1, for n by 2 there will be mx2, for n by p there will be mxp. So I am considering intersection of those members. So let intersection of all mx i's, I vary from 1 to p, I am naming it as m. And since this x is fixed, so every time x will be a member of this. So x will definitely be a member of m. X will definitely be a member of m. Now, let us move ahead. This A is a subset of union, and if I name it as n, then note then that n and m are disjoint. N intersection m is phi. This is very clear, because here you are taking this set and finite. On the other side, you are taking several sets containing x, and then their intersection. So intersection will be smaller. Since each of these one is not intersecting the corresponding member over here, so the intersection will also be not intersecting this union. So n union m will be phi. N union m is phi. Your A is a subset of n. A is a subset of n. N intersection m is phi. So what the name I have taken in the starting for the set that for which complement is to be proved, this is A complement. So A is a subset of n, means n complement is a subset of A complement, and from here m is a subset of n complement. M is a subset of n complement. N complement is a subset of A complement. From these two, you can directly have that M is a subset of A complement, and your X belongs to M. X belongs to M. You have taken an arbitrary element X from A complement, and now you have introduced M such that X belongs to M and M is a subset of A complement. Now look at what M is. Each of these mxi's is an open neighborhood, that means open set. And we know that finite intersection of open sets is open, so that means this M is open. So between X and A complement, we have introduced an open set M such that M contains X and M is a subset of A complement, and it proves that A complement is open. And once A complement is open, definitely A will be closed. So that was the result to be proved, that a compact subset of a Hausdorff space is closed. We have taken a compact space, we have taken a Hausdorff space X top. We have taken a compact subset of A. We have shown that A's complement is open, that means A is closed, and that was what we required to be proved. So here I am going to stop this video. Wait for the next video. Thank you. Thank you once again.